Okay, welcome everybody to the first workshop for beginner competitive programming. We're really excited to have you here. Here's a link to the slides. So if you guys are not already on the slides, we'll take a second here to just let me know if that link works. The portal code is Euler Lake. The event should be on the membership portal and you get 20 points for attending. And yeah, okay, let's get started. So, before we get into some of the cool problems we have in place for you, let's quickly go over what is competitive programming and what that looks like at ACM ICPC. So, yeah, just to get you guys thinking about why you're here and why you're doing what you're doing. So what is competitive programming? Well, this might be new to a lot of you, or maybe not, but it's a race to solve the greatest number of algorithmic challenges as quickly as possible. It's unlike a hackathon where you're sort of developing some software engineering project that you need to do in 48 hours, but instead you're trying to build a time efficient as well as a space efficient solution to some common problem. And these problems are sometimes rather interesting. Sometimes they're coded with a lot of flavor text to maybe deceive you or to make it sound more interesting. But the emphasis is more on problem solving than software engineering. And you'll get a taste of what that is for those of you who are new to CP with the problems we have in store later. And yeah, so the solution normally involves some cool trick that you're probably missing or probably looking out for, and that's why people are so interested. It's just really exciting finding that one cool trick. Okay, so competitive programming at ACM ICPC takes the following journey. We start with Intro to CP in fall, and this journey has kind of been revamped. So a lot of you who have been with ACM ICPC before, like last year, this might be slightly new to you. But last fall, we came up with our new track, Intro to CP, where we focused at slightly easier problems and had a more beginner-friendly exposure to competitive programming. This naturally segues into beginner CP, which is what you're here for now. And we still focus on beginner-friendly themes, but we go slightly more in depth into some algorithms and some data structures that we didn't explicitly cover in Intro to CP, like graphs, trees. And we actually have an exciting new topic this time on game theory, where you're trying to compete, where the problems usually involve competing with other players who play optimally. So how do you get the most optimal solution? From beginner CP, you can naturally segue into CodeSprint LA, which is our own in-house competitive programming competition organized in spring. Yeah, we have problems that are on the level of beginner CP and some slightly harder problems, but our goal with beginner CP is also to prepare you for CodeSprint LA. Our other natural goal with beginner CP is to expose you to competitive programming in general, and just get an idea of what competitive programming looks like out there. So from CodeSprint LA, we naturally segue into the following things. You can join the ICPC team to represent UCLA in the annual programming contest. You can also go to advanced track, where we cover more advanced things such as topological sort, biconnectedness, and strongly connected components and graphs, things like that. A lot of graph stuff and a lot of cool things on strings, etc. We also might have something known as an intermediate track, which we might do next spring. That's again the natural segue of beginner CP, where you can experiment with slightly more advanced topics, but that's TBA. You can also go to more programming contests. You can do programming contests on your own time, like CodeJam, which has some really well framed problems and would really give you a good idea of what competitive programming looks like out there. But most of all, if you're not interested in competitive programming in general, like that's not something you probably want to do, it just makes you a better programmer and a better solver. It just it gives you that big brain. So hopefully at the end of this workshop, even if you're not super interested in CP in general, you would attend our workshop just to get a good idea of just to get a good idea of algorithms and CS in general. Okay, so with that, welcome to beginner CP. We're an independent continuation of Intro to CP, and what that means is that people who attended Intro to CP, this is the perfect place for you. We don't naturally assume stuff you've done in Intro to CP, but if you've done Intro to CP, you're going to be perfectly comfortable here. Our general goal is to expose the UCLA community to competitive programming. So that's you're the UCLA community here. We want to make you better and more rigorous about problem solving. So, sometimes people think problem solving is just about finding patterns and seeing if that pattern extends to other cases. And sometimes that works, but you want to know why your pattern or why your solution actually works. And that's what we want to do a little bit with beginner CP. And we also want to prepare you for CodeSprint LA. So this was a goal mentioned last time. We want you to, the goal of CodeSprint LA is to be at the same level of beginner CP or slightly harder. And with that said, though, anyone is welcome. It's still beginner friendly, and we just have more interesting topics. Anything we cover in the workshops, you're more than happy to ask us about it. We should mostly cover all the grounds before the problem is tackled, so you shouldn't have any problem following up. So this quarter we have the following schedule. This workshop's going to be some ad hoc problems. We're going to look at 3 problems in a bit. The next 2 workshops are going to be focused on dynamic programming, which is a very vital concept, not only for competitive programming, but generally CS and interviews and whatnot. We're then going to move on to graph searching, followed by trees. And in the last week, we're going to have game theory. Sometime in between, I believe after dynamic programming, we're going to break for midterm. So we're going to have dynamic programming in week 3 and 4, and then graph searching in week 6. So week 5 is your midterm break. That might be moved around a bit, but that's a tentative schedule. And at the end of all of this, we're also going to have a mini contest where we test you, where you test yourself on things you've learned during the quarter. Okay, so with that, let me introduce the team before we move any further. So I'm Rohit. I am a 3rd-year CS and math major. I got into competitive programming and ICPC in general just because I was really excited to interact with the people who are on the team. I wasn't someone who was into competitive programming in general, but these are the group of people I wanted to hang out with. So it's been an amazing community. I've had a lot of fun, and I've had the opportunity to lead beginner CP this quarter. With that, let me have the team introduce themselves.
Hi, I'm Lenny. I am a 2nd-year computer science and applied math major. I attended Intro to CP last quarter, and I really enjoyed it. So now I'm here joining ICPC, and I hope to teach you guys some more about programming and problem solving, and I hope that it'll be fun for you all.
Hey guys, I'm Rishi. I'm also a 2nd-year CS major, and I got into competitive programming last year through the beginner track. And yeah, I'm also excited to be teaching this workshop again after teaching Intro to CP last quarter.
Hi, I'm Raya. I'm a 3rd-year math and computation major and an intern for ACM ICPC. This quarter, I got into competitive programming last year doing this workshop, and it was fantastic. And so I just wanted to stay and keep hanging out with these people, and I hope you will do the same.
What's up, everyone? I'm Alvin. I'm a 3rd-year CS major. I've been in ICPC for a year now, and I've mainly been teaching in the interview track, like workshops. You may have, if you went to interview track last quarter, you may have seen me. I was leading it with Bill. This year I decided I want to switch things up a bit and learn a bit more about competitive programming. And I want to teach you guys about competitive programming. So now I'm here.
Thank you. So I hope something you took away from that is we're basically, you guys, I mean, we're not like some CS competitive programming gurus. We're learning with you here as well, but hopefully, we have a little bit of experience and we'll take you through this pretty interesting and cool journey. All right. So with that, let me tell you a little bit about how the workshops are going to look like, and then we'll slowly start to get into what we have planned for the day, for the hour, I guess. Okay, firstly, we have a 2-hour slot, but the first 60 to 75 minutes of that are going to be presentation. And this presentation usually involves teaching you some sort of algorithm or algorithms, and with some example problems to strengthen what you've just learned. These example problems are going to be Caddis problems, and we're going to talk about Caddis a little bit in a bit, but it's basically what we use for hosting our contest. We're going to have weekly contests, but more on that in a bit. And so then we do have our weekly contest, and the next hour of our workshop is dedicated to starting that weekly contest. This is a space where we break you out into breakout rooms, with the officers, and you could ask each other or the officers about the problems. The idea is to work collaboratively. You're not really competing against each other for these weekly contests. We want you to work together and solve it together. I think that's where the true learning happens. So yes, we do want to stay. We want you to stay for the hour and interact with the other attendees and officers. And we have our Discord forum here. This Discord forum is purely dedicated to the material covered during these lectures. You're free to ask us any questions about CP in general, the workshop content. If you want us to check your solution, maybe you could drop us a DM. But if there's any code snippet that you want to talk about, you could please feel free to put it in the forum, and you guys could probably collaborate and work together. And yeah, so this is something we're trying 2 new things this quarter. The first thing is a point-based system to encourage participation. We really want this to be an interactive session. So you get 1 point for even just turning on your video this workshop. There's no pressure. The point-based system only. So basically, the person with the most number of points at the end of the quarter will get a free Amazon gift card. And you just get 1 free point for turning on your video. So if you want to do that, it's great. It'll be nice for all the officers. It'll be nice for us. It'll be nice for you. It's hard to find some sort of community on Zoom, so it'll be nice. And one more thing, yeah. And then I'm gonna, we have a couple of questions that we just throw out in the audience. So you're free to unmute yourself or put it in the chat. Every time you do that, you also get 1 point. So please let's have this bi-directionally. Yeah, I don't know. Did anyone turn on the video? All right, we're getting some free points today. Awesome, glad to see you guys. Okay, another thing we're trying out this quarter, and I hope you will take advantage of this, are mini problem editorials and office hours. And we realized that a lot of people who did the contest, the contest in Intro to CP, maybe got stuck on a problem, and the only way they could get unstuck was whether they had some help. And that's natural for all of us. And sometimes, and we did not make ourselves super approachable. The only place we were available were Discord DMs, and maybe you're busy with other things, and maybe you just don't know who we are. And it's kind of daunting to send us a DM. So this time we have office hours where once a week we dedicate a 2-hour slot where we're available on Discord for you to ask us questions regarding the contest. And once the contest ends, we also post like mini editorials, which are basically small problems, solution descriptions, where we write a mini paragraph about how you could go ahead solving those contest problems. So you basically have the office hours, which is during the contest to ask us questions, and then the editorial to finally help you solve the entire problem. We hope these really encourage participation during the workshops, during the contest. The contests are not meant to scare you away. They're just a place for you to practice. And if you're ever stuck, this should be the perfect way for you to reach out to us and actually finally solve it. And hopefully by the end of the workshop, you guys are more experienced. The idea is not mastery within a single week, obviously not, but hopefully mastery over the entire quarter, some sort of mastery. Okay, so before we go any further, I have a quick poll where I would just want to know what your experience with competitive programming is. So, I just want to make sure I have the pacing right. It's completely anonymous, so just feel free to mark it honestly. Yeah, let me go ahead and launch it. Okay, I think all of you filled it out. Thank you so much. It's pretty interesting to see. A lot of you are new to beginner CP, so it's going to be fun. A lot of you also have no experience, which is awesome. That's exactly the kind of people we want to cater to. And there's someone who's had 1 year of experience, so perfect. I hope this is a perfect refresher for you, and you get a good you just get a good refresher on the topics. We have some challenging stuff in line as well. All right, with that, let me go ahead and end the poll and move on. Okay. Great. So sorry, we have another poll, I just realized. And this is about workshop time, because we realized Friday might not be the best time for a lot of people to attend. We realize you might have other commitments. You might have a lot of CS discussions. I'm assuming a lot of your CS majors, and it just might be a lot of things. I realize a lot of you might be weeps and have anime night at 8 p.m. I get that, and it might just be a lot of events together. So we do have an alternate time. That's Friday 7 to 9 p.m. That may or may not work better for you if you have discussions later at night, or Wednesday 7 to 9 p.m. So let me just launch a poll here. You're allowed to select more than one option. So just select whatever options work for you. And hopefully we can work something, work something that works for the majority of you guys. And that'll be the workshop time, which we'll launch from next week. So let me go ahead and launch that poll as well. Okay, that was fast. Thank you so much, guys. I will let you know what the decision will be very soon. You should see it on the Facebook group. You should see it on Discord and everything. But thank you for filling that out. All right, so thank you. With that, let's move on. And we'll just spend a little bit of time on the basic setup you should have for competitive programming. I realize a lot of you are new to it, so let's go over this slightly slowly. But firstly, it's extremely important to use pen and paper. And by that, I do not mean you should write code on paper, but often when you're brainstorming and you're trying to visualize something, it's really easy to draw it out. And sometimes when you're drawing it out, that's when you get your breakthrough idea, where you actually notice some sort of edge case, you maybe notice something, you notice some pattern that's working and you try to prove it. And what we basically mean here by pen and paper is something to just jot your ideas down on, something to draw and something to maybe just write out small things on. It's extremely important. Sometimes you don't get the same feel when you're typing. You want to use your hands more actively. So we really encourage keeping a pen and paper on the side. It really helps you to visualize your thoughts. Next, speak in C++. And we encourage this for many reasons. Firstly, it's a very fast language, and competitive programming is all about optimizing for time and speed, for time and space. And you want to ensure that your solution, runs in a certain time bound. And C++ is a fast language. It's relatively low level, so that allows for faster computation. It is also the language of instruction at UCLA, so you already should have some experience with syntax, or if not, if you learn it over the span of this quarter, then with the workshop, it should help you with your other classes at UCLA. And it also contains a lot of standard libraries that help you implement a lot of data structures and algorithms. We're going to go over something called vectors today, and that's already built into C++ that help you store a list of items really easily. Other alternatives include Java and Python. These are super useful for handling big numbers. Sometimes they're better for parsing input. But for this workshop, we're going to make sure you can do everything in C++, and we're going to make you better programmers in C++ as well. So from the inventor of C++ himself, yes, please use C++. And we're just going to happily oblige because that's what we've learned to do. Awesome. If you guys ever feel like there's an easier way to do it in Python or something, that's okay, but we want you to get better experience with C++. C++ is a great language for competitive programming and just CS in general. Okay, and next up, what's your compiler or editor setup? Well, normally if you've done C++ on your computer before, you probably have a new compiler or you have Visual Studio Code, that has, I believe, I'm not sure what the Windows equivalent is, but you probably have that. And that's okay, that works really well. But for those of you who do not have it set up, you can actually use this online IDE called Replit, and I'll drop the links on the next slide. But Replit basically has everything that we were going to include, all the standard libraries we need for our workshops, and it's just going to streamline the entire thing. So Replit's a great way to run your code and make sure that everything's compatible. For those of you running on Mac OS or Linux, you need most of our, to avoid including a lot of standard libraries, you can include this one library called bits/standard_c++.h. We'll have more info on that in the breakout rooms, or like when we start the weekly contest or the example problems. But sometimes that is not available on your system and you need to install it separately. But if you're one of those people, feel free to ask us during one of the breakout rooms and we're happy to help you out. So for Replit, if you want to use C++, you can click on that first link over there. That should take you to an empty REPL, I believe is what it's called. And over there, you can code whatever you like. We also release templates for all the problems we're going to cover today. So you can directly just copy paste the code of that template and put it in Replit and run it. And there's a run button right there, right over here. And once you do that, you can copy paste the sample input and output. And if that doesn't make sense, we'll get to it in a second, and run it to check whether your answer is correct or not. We also have REPLs for Python and Java, but hopefully we're not going to be needing these. Okay, so with that, let's get right into it. But before that, does anyone have any questions about what we've covered so far? You know, what beginner CP is aiming to cover, why you're here, things like that. Feel free to unmute yourself or put it in the chat. I'm looking at the chat as well. Okay, happy to hear it in some sense. Sure, let's go ahead. So, okay, so the first thing you need to have an account on is Caddis. Actually, the only thing you need to have an account on is Caddis, which is Caddis is basically a virtual judge that hosts all the problems we're going to be using for this workshop. It allows us to easily create a leaderboard where you know, those of you who are participating in the weekly contest, and hopefully all of you, will be kind of ranked based on, it'll basically simulate an actual programming contest. And you know, these rankings really don't matter. You know, they're for personal improvement. Although we will be raffling, you know, gift cards at the end of the quarter for those who you know come up, you know, overall have like on average, you know, come on first, second, and third, I believe, based on how much money we have to give out. So please first create a Caddis account if you haven't already on the following link, and please tell us your username. I'm going to wait for the responses to start filling up. This is important because Caddis contests are public, and I think anyone can join. While people usually do not, we want to ensure that we know who's attending our workshop and who is some random person on the internet. Although those people are very few, and in fact, pretty much zero. I don't think we had any problem last quarter, but just to make sure. And yeah, so we'll just give you 5 minutes to fill that out. While you're filling it out, let me just quickly tell you a little bit about Caddis. So Caddis basically, the way a competitive programming problem looks like is you usually have this problem statement followed by the sample input that tells you, you know, like the problem statement describes what the problem is going to look like. You know, what are you aiming to solve? And the sample input tells you how exactly are you taking in the constraints to the problem, or how exactly are you inputting the data on which you need to operate on. And the sample output basically tells you how you need to print out the resultant answer. And you know, we'll get a little more experience with that when we get to our first problem in just a few seconds. But yeah, and Caddis as a virtual judge has something called verdicts, and verdicts tell you how your solution did. For example, if your solution passes all the test cases, and test cases are something that's run on your program to check whether you've been doing it right. If you get an AC, which stands for accepted, that means your solution's passed all the test cases and you're good to go. There's some other verdicts like time limit exceeded. You know, your solution's probably taking too long and it doesn't satisfy the constraints. For example, usually these programs are supposed to run in a second or maybe 2 seconds, depending on the program. And if it exceeds that time on, you know, maybe really large inputs, then we have a problem and you want to come up with a more efficient algorithm. We also have a verdict like memory limit exceeded, which is usually really rare, but sometimes you might exceed the amount of total memory your program is taking, and you'd want to avoid that. You know, some other errors include compile time errors. You know, maybe a program didn't compile. Runtime errors. It probably accessing some null pointer. So I don't know what not. Accessing an array out of bounds. Things like that. Yeah. So sorry. I'm going to quickly look at whether responses started filling into the form, and then we can go ahead to our first example problem, which should give you great experience as to how to work with Caddis. Okay, we have about 9 responses. I'm going to wait for, I believe, 5 more. For those of you who were part of Intro to CP, we would like you to fill this form out again because it's just one central place where we can see all the responses. I'm just going to wait maybe 1 more minute and then we can go ahead. These links should be available in the slides. So, you know, whenever you register, you can go ahead and add your information here. I'm just going to wait 30 more seconds. Okay, I'm going to go ahead. For those of you who haven't filled it out, hopefully you do. it just helps us keep track. And it also really helps when we want to give out those gift cards at the end of the quarter. Okay, awesome. So with that, let's get into the first problem, problem A, which is called cooking water. So you should, that link should link you to all the contest, all the example problems for this workshop. Just click on problem A, that is the first one. And we'll just take some time to get familiar with the layout. I realize a lot of you might be new to Caddis. There should be a submit button on the top right. Unfortunately, I don't have slides to show you this right now. But once you click on the submit button, you should be able to copy paste the code you've been working on and submit right there. We recommend first running your code on Replit because you don't want to get a wrong answer. You're penalized for wrong answers, and the penalty depends, but usually it's quite major. So you want to make sure that your solution at least compiles correctly before, otherwise that'd be unfortunate. So one of the things you should note about competitive programming is that it's unlike interviews or like lead code where you're just given some function body to implement. You actually need to implement the whole program. So the main routine, the input, output, everything needs to be done. And to help you out with the input, output this first workshop, we're providing templates. And that link to the template should take you to a GitHub repository where you should find, templates for all the problems. For this one, it should be cookingwater_template.cpp. And that should do the input and output for you. That code compiles perfectly in Replit, so hopefully you have no problems with it. Okay, so I'm going to give you 5 minutes to read the problem statement, or maybe a little lesser, and then we'll go over the sample input and output together. Hopefully, so you get an intuition of the problem. Then we're going to give you about 5 minutes to about 3 or 4 minutes to just think about it. We don't expect you to code the entire thing in the limited time we give you, but for those who could code it, that's amazing. Yeah, and then we'll also, after 3 minutes, we'll probably give out some hints, spend 2 minutes there, and then we'll get into the solution. Yeah, awesome. Let me address something that's going on in the chat. Do we click to join the contest? Yes, thank you. I should have mentioned that. Yes, please click to join the contest so we know who all is participating in the example problems. You're also free to unmute yourself if you have any questions, even about the problem. Yeah. Yes, also just please ignore problem B and C. We'll get to that eventually.
I have a question.
Hi, yeah. Who is this?
The format of this is it gives us sample input 1 and sample output 1, right? Do they correspond with each other? They do, right?
Yes, they do. So the sample output 1 is the answer you should give out when you input sample input 1.
Okay. Wait, I'm actually kind of confused. Am I like, wait, like, is it the same interval of time has passed? Then it's true?
I see.
Hold on.
Sure. Okay, this might be actually a good point. I think hopefully a lot of you have read the problem. Let me just go over the sample input, and I think that'll clear things up. Okay, so let's check it out. So let's look at the first input. Here we have 2 ranges, 1 to 7 and 5 to 5. And we have the sample output 1, Gunilla has a point. First thing to notice is that you have this range from 5 to 5. How does that even make sense? Well, notice how the problem said start of the 8th second and end of the bth second. So what this is telling you is the start of the 5th second and end of the 5th second. So you have that entire 5th second that's still valid. And here Gunilla has a point because Gunilla has a point is whenever there's a possible range of boiling points. And here, one point where the pot could have actually boiled is a 5th second, because the 5th second is between 1 and 7. And what the problem tells you is that Edward did not see the pot boiling before the 1st second, but definitely saw it boiling after the 7th second. So that definitely includes the 5th second where he wasn't looking. Similarly for 5-5, Edward did not see the pot boiling before the 5th second, but saw it boiling after the 5th second. So the pot could have been boiling still at the 5th second. So there's this one point that is shared by all the ranges. Similarly, you can kind of so it's possible because you have the 5th second. You can kind of reason why for the other sample input there's actually no point where the pot could have been boiling in all the cases. For example, if you consider maybe the 5th second, the first two agree, yes, the 5th second is a possible point for in which the pot was boiling. But the third input tells you, the third range from 7 to 8 suddenly tells you that the pot was not boiling before the 7th second. So the 5th second is suddenly a wrong answer. And you could reason out with all the possible values that there's actually no value that works for all the ranges. So how do you find, how do you know if there's a value that works for all the ranges? And that's kind of the goal for this problem. And let's give you 2 more minutes. Think about what I just said, and then we'll go through the solution together. I'll throw it out to the audience first, and then we'll go through the solution together. Yes, the seconds are inclusive. Well, yes. So, I mean, technically the problem is kind of weirdly stated, but it's saying that before the 5th second and after the end of the bth second. So, yes, in some sense, you could just consider them as inclusive. Yeah, just to remind you again, we don't expect you to code the entire thing. We realize we're giving you really little time here, but hopefully these problems are sort of instructive in telling you how interesting or maybe how widely ranged competitive programming problems can be. And that's kind of the idea with our ad hoc workshop. Welcome this first session. All right, just to get an idea of how people are doing, let me go ahead and launch another poll. And we're going to have a lot of these polls. Just gonna wait a couple more seconds for people to fill it out. We have, I think, another 4 people who've yet to fill it out. Then I'll see. Okay, cool. Let's wait maybe 30 more seconds, and then let's get into the solution together. Don't worry if you didn't get it. These the idea for the example problems are for you to get. You're not supposed to get it immediately, and we realize we've just given you like 5 to 7 minutes to do it, and that's probably too less. But hopefully you go, walk through the solution with us, get the solution, and then are able to tackle the contest problems. And that's kind of the idea. Cool. So let me go ahead in 5 more seconds. Let's wait 5 more seconds. Okay, so let's go through a solution together. And yeah, okay, firstly, actually, I should have shown you some hints. Hopefully you looked at the slides, but I'm sorry I didn't go through these. But given the data, can you determine the range of possible boiling points? That's kind of your goal here. So if there's like a valid range, then your answer is gonna have a point. If there's no valid range, then Edward is right. But yeah, when can you not? When do you know something is wrong? For example, looking at sample input 2, how could you tell something was wrong? Something seemed off, where if you tried any possible value, one of them always contradicted. But how do you find that? How do you find that error? And yeah, one point to note is that remember that the boiling point is the same across all the data. So you're not worried about different boiling points, which is kind of in the problem. And before I get into the solution, maybe I'll open it up to the audience. Did anyone have any ideas? Even if people got it, people didn't get it. What are you thinking about? What is your approach towards the problem? You can put in the chat. You can unmute yourself. Okay. Do we have to take the max of start of intervals and min of end of intervals and see if max is less than min? Yeah, that's actually a great idea. And that's actually what we're going to do here. Do you have an intuition as to why that's the case? I mean, I realized it might be hard to explain, but you give it a shot if you like. But that's you drew it out. Okay, great. And that's kind of what we're going to do with our solution here. And hopefully, you see it more rigorously why it's true. Awesome. I like that. Let's go with that. Thank you, Sid. Okay, so notice that for each input range, the pot is not boiling before the 8th second and is boiling after the end of the bth second. I mean, I'm just restating the problem here. And we're going to try to determine the range of possible boiling points. And if this range is something we can actually determine, then Gunilla has a point. But if this range is not possible, then Edward has a point. So suppose this range is xy. So what we mean by xy here is that the pot is boiling before the x second, and it's not boiling before the x second, but it's boiling after the end of the y second. We're trying to make this range as small as possible so that it satisfies all the inputs. As Sid said, x is actually going to end up being the maximum of all the a's, and y is going to be the minimum of all the b's. And this doesn't have to make sense. You don't need to look at these equations, but let's go through an example to see why this makes sense. So suppose you had the following. Suppose we're looking through sample input 2, and we look at the range 4, 6. So these are just boxes representing different seconds. And the seconds go from 1 to, in this case, 1,000, because they say that n is only between 1 and 1,000. And we look at the range 4, 6. So as soon as we get the range 4, 6, we know that all the other entries cannot possibly be where the cannot possibly have the pot boiling. I mean, cannot possibly be where the pot started boiling, because it clearly told us that the pot is started boiling between the 4th and 6th second. So now our new XY, our new range for when the pot could have been boiling is 4 and 6, which is exactly where the arrows are pointing. Next, we get the data for 8. 4.8 tells us that the pot was boiling before the 4th second, was not boiling before the 4th second, but started boiling sometime between the 4th and the end of the 8th second. But hey, we already know from 4.6 that the pot could not have been boiling in the 5th and in the 7th and the 8th second, because it started boiling after. Sorry, it could not have started boiling on the 7th and the 8th second, because the pot was clearly boiling already at the end of the 6th. So those two entries, like the 7 and the 8, tell us no new information. And in fact, that entire entry 4.8 told us no new information. You kind of realize how the 8 was in fact larger than the 6. So it was telling us nothing new about when the pot could have been boiling, or when it could have started boiling.
Rohit, I think your slides aren't working, the screen share.
Oh, I am sorry. I think I had it paused.
Okay.
Thank you.
Yeah, it's working now.
Let me quickly go over the slides. Yeah, hopefully you guys were following with the slides online, but I'm sorry, I should have unpaused. But yes, basically what I was saying, once you have 4.6, you cross out all the other entries that they're no longer possibly a point where the pot could have been boiling. In 4.8, you have this range of values, but again, the 7th and the 8th second are already values in which the pot could have not started boiling, because it tells us clearly that the pot started boiling before the 6th second. And finally, we have the range 7.8. 7.8 tells us that the pot started boiling sometime in this time. But wait a minute, we already know that the pot was boiling sometime in this time. So there's no way, it doesn't make sense for the pot to have actually been boiling at this time, because we've already crossed them out. So what's going to happen here is that if X is the maximum of all the A's, which means like we're trying to minimize the range as much as possible, X would end up jumping to 7. And X is basically telling us, what is the maximum point at which the pot had not started boiling. And at this point, it seems like X has sort of exceeded Y, which clearly doesn't make sense. I mean, you can't have a pot to have not boiled before, to have started to boil before it even did not boil. That doesn't even make sense. And what I just said was super contradictory. So at this point, you kind of know that that it's not possible for there to have been any one single point where the pot always boiled when Edward was looking away. So to kind of further drive that point home, let's look at the code together, and that'll give you a better intuition. So over here, we set like a lower and upper bound, which kind of tells us, what's the lowest possible value for which the pot could have been boiling, and what's the highest possible. And that's, -1 and 1001. In this case, that works because they clearly told us that the pot only boils in that interval. And we then take in all the possible data ranges. So we go from I is equal to 0 to I is less than n, and we take in all possible value, all the data ranges, and we clearly just take the maximum of all the A's and the minimum of all the B's. And that's kind of what we're doing here. So if A is greater than X, so if the new entry that we got is greater than the current entry that we have, then we end up setting the current entry to this new entry. And that's kind of what we're doing here. So this is the maximum code, and this is the minimum code. We then clearly just check, as Sid said, whether the maximum is smaller than the minimum, in which case, if X is less than or equal to Y, and this means it's a valid range. You can't have a range in which the starting interval is a starting entry is greater than the ending entry. That doesn't just make sense. And in this case, if there's a valid range for which the pot could have been boiling in, then Gunilla has a point. Else we say Edward is right, and that's kind of the idea. I would have liked to take questions. Unfortunately, we are short on time. So we'll postpone those questions to the breakout rooms that happen after the workshop. We'll have one dedicated just for the example problems. And with that, we'll move on to our next problem. And unfortunately, this might just be one problem after another, but all of them should give you a solid intuition of some cool, interesting problem in competitive programming. And hopefully those are instructive. So I'm going to give it off to Lenny, who's going to take you through problem B.
All right. So the link to the problem is on the slides, and the template is also there. And you can just maybe read over the problem statement and look at the sample input and output for a few minutes, and then we'll review the sample IO and go over the solution. All right, so let's just take a look at the sample input and output now. So here is the first sample input, which is WWBWBB. So you have 2 white stones, followed by 1 black stone, followed by 1 white stone, and then 2 more black stones. And notice that the problem statement says that basically the stones are arranged in a circular style. So the very last stone given is adjacent to the very first stone. And yeah, so here's the layout of the stones in this first example. And what we can do here is our first operation can be take this subsequence of stones. So here's 2 white stones and 1 black stone. So there's 1 more white stone than black stones. And you can replace this with a single white stone, because the problem statement says that you can take any subsequence where there's 1 more white than black and replace it with a single white. And so here's what happens after we do the replacement. And what we can do now is, again, take another subsequence where there's 1 more of 1 color than the other. So we can just pick some random subsequence like this one. There's 2 black stones and 1 white stone, and we can replace this with a single black stone. And so this is what it looks like now. And notice that here we have balanced the stones because at the end we end up with 1 of each color, which is why the sample output for this problem is just 1, since we can balance it. And now let's move on and take a look at the second sample input output. So now we have 4 white stones followed by 2 black stones and ending with 1 white stone. So in total, there are 5 white stones and 2 black stones. And here we can take another subsequence. So here we just take these 5 stones. Notice again that there's 1 more white stone than black stones. And what we do is just replace it with a single white stone. And we end up with three white stones. And because there's no more black stones left, we can't do any more operations. And we're kind of just stuck with this at the end. So what this means is that it's impossible to balance out all the stones, which is why our output would be 0, meaning that it's impossible. And notice that no matter which subsequence that we take, for example, we can take these 5 instead, we'll still end up with 3 white stones. Or we can take maybe like a smaller subsequence, but after some trial and error, you'll notice that no matter what, we'll always end up with 3 white stones. So it's going to be impossible to balance these. And yeah. So I would like to give you guys some hints as to how to solve the problem. So firstly, every time that you remove a set of stones, the difference between white and black stones remain the same. And this is because every time you remove a subsequence where there's, for one color, there's 1 more than the other color, and you replace it with a stone of that color which has more, and you'll notice that indeed every time the difference between the total count of white and black stones is going to be the same. So for example, we can see in this sample input output, we start with 5 white stones and 2 black stones. So the difference is 3. And we do an operation, and after this, the difference between white stones and black stones is still 3. There's always going to be 3 more white stones and black stones. And you'll have to notice that for no matter what kind of stones you're given, it's always going to happen like this, where the difference between the colors of 2 colors of stones will remain the same. And next, you can always perform a non-trivial operation somewhere as long as you have both type of stones and more than 2 stones. So as long as you have stones of both colors, you can always perform an operation. Yeah, this is pretty obvious. And yeah, so I guess I'll give you guys a few more minutes to think about maybe coding up a solution and just think about how to solve it. And then we can move on with it. All right, so now it's time to take a look at the solution. So actually this problem is kind of a trick question, because in order for the stones to be balanced in the end, you need exactly 1 white stone and 1 black stone. And the difference between both types of stones is always going to be 0 in order for you to balance it. And if the difference is not 0, then it's always impossible to balance it. So basically, if the number of white stones does not equal to the number of black stones, then it's actually impossible to balance the stones. And as we said earlier in the hint, the difference remains the same after every operation. So we want the difference to be 0, because at the end, 1 minus 1 is just going to be 0. So you always want the number of each color to be the same. So is it always possible when the number of white stones equals to the number of black stones? Yes. And yeah, so this question, it looks a little bit more complicated than it actually is, but the solution is going to be pretty simple. You just want the same number of stones for each color. Yeah, so you can always find an operation to perform as long as you have both colors of stones, and every operation keeps the difference the same. So our solution is just to check if the number of white stones is equal to the number of black stones. And here is the implementation. So here's just taking in the input. We're given a string and we store it in a string called stones. And here we have the count of white stones, which is represented by W, and count of black stones, which is represented by B. And so for every element, or sorry, for every letter that we're given, if it's W, then we increment the white count. Otherwise, we increment the black count. And at the very end, here's where we output the answer. So if white equals to black, then we output 1. Otherwise, we just output 0. So yeah, this is a pretty simple solution. And yeah.
All right, so hopefully you enjoyed that problem. We have one more thing in plan for you during this workshop. We're sorry it's kind of running late. I know we said 60 to 75 minutes of presentation, and then followed by you asking us questions. But just bear with us for one more problem. It's going to be fun. And before we get into that problem, though, let's get some background on vectors and something called sorting. So vectors are basically this data structure, and it's sort of like an abstraction of an array. So if you've taken CS31 before, you know what an array is, but it's basically something that can hold a list of items. And vectors kind of allow you to store an arbitrary size list of items. And you might have seen, if you used an old version of C++ before, that array sizes need to be fixed at compile time. And C++ 11 and 14 changed that, where you could have variable array sizes. But vectors are sort of more powerful because they come with these member functions, like pushing elements to the back of a vector, for example. And there's some really nice declaration/initialization structure where you can set a default value for all the items in the vector. For example, if you wanted an array of 10 elements, all that were 1. So you wanted an array of 10 integers, all 1. To do that in an array, you first need to create an array and then loop through the array, setting each element to 1. But in vectors, there's some really convenient syntax where you can just do it in one line while declaring the event, while initializing the vector. And we'll get to that in a second. So vectors are super nice. And for the entirety of this workshop, we're going to be using vectors. Okay, so let's go over some syntax real quick. And you can refer to these slides later to see, because some of it might be new. So suppose, like I said, you wanted to create an empty vector, or you wanted to create a vector of n elements. N was is an integer that we had stored before, but we want this to be a vector of strings, and each string should have a default value of a. So each string is a string with just one character, which is a. And to create this, we actually have this weird sort of maybe newish notation, newish syntax where you have vector, angular bracket open, string, angular bracket close, the name of the vector, open parentheses, the number of elements, comma, the default element. And similarly, you could do this for integers. So you could replace string with integers, but you can also explicitly list out the elements. So for that, you can use a curly brace, which is very reminiscent of arrays. And you can list out the array elements explicitly like you do in a normal array. Now you can also add elements to vectors easily, like I mentioned before. And the function signature for that is pushback. Pushback followed by the type of element you want to push. Note, just like arrays, these are all homogeneous. So if you can only have an array of integers. You can't mix an array, or sorry, a vector of integer and strings. They all need to be integers or all strings. You can also pop back. So pushback essentially pushes that integer to the end of the array, to the end of the vector. And if you want to push off, and if you want to pull out or basically pop out the last element of the vector, you can use pop back. You can also access vectors. Sorry, you can also access vectors just like you do arrays with bracket notation, where you say vec2 bracket 0 is equal to 24. And this allows you to both access and modify. So just like arrays, and you can modify the 0th entry of the vector and replace it with a 24. More on vectors. So you can also get the size of a vector, which is something you cannot do in arrays. So this is super nice. And since you can arbitrarily size them, this gives you the exact size of the current number of elements in the vector. And you can just do vec2.size. There's something called iterators, which we're not going to get into too much, but you should just know them for syntax. So vec2.begin kind of points to the beginning of the vector vec2. So I mean, if you've done CS31, you know what pointers are. Even if you're not super comfortable with pointers, you're not going to need this anywhere except for just writing it out. You don't need to know how it works. Vec2.end kind of points to just after the end of the vector. Again, this doesn't need to make sense to you. Just think of it as the beginning and the end of the vector for now. And these are super useful, we'll come to those in a second. But suppose you wanted to iterate through all the elements of a vector. Well, you could do it from 0 to the size. And since vectors and both arrays, everything in C++ is 0 indexed, you go from 0 to just 1, just to n-1, which is size -1 in this case. And you can print out each element. That is one way of doing it. You can also use iterators, and I urge you not to focus too much on the syntax. It's not important. But for those of you who are kind of interested in how to use iterators, they kind of work like pointers. So you can access the value that an iterator is pointing to by using the star operator, and you can move to the next element in the vector by doing it++, where it is kind of like our pointer here. Some of you might be seeing this new keyword auto, and auto is this way of C++ to infer the type. So suppose you didn't want to tell C++ what the type is because it might be too long. It might be something you don't want to remember. It's like Python where you can say x is equal to 3. You can just say auto something is equal to something, and it'll try to infer the type based on the value you gave it on the right-hand side. Okay, so vectors, just think of it as arrays. No big deal, just some new syntax. But we're going to look at something called sorting. And sorting is I guess you could say an algorithm for putting things in some order, or like a concept of putting things in some order. And example, you could sort an array of integers to put them in increasing or decreasing order, or maybe sort an array of strings and put them in lexicographic/dictionary order. And sorting can make a lot of problems simpler. Sometimes the problem is really demanding some sort of structure, and you want to parse the input. Like maybe you have a list of numbers in a very specific order, and that's where sorting can become super useful. So, for example, do you want to look at your list in a specific sequence? And this might seem random, but the next problem is going to be using sorting. So let me just give you that hint already. Sorting implementation, some of you have done CS31, might have gone over stuff like insertion sort, bubble sort, selection sort, things like that. Maybe some of you have heard of quick sort, heap sort, maybe. But really, in competitive programming, you can't be bothered to implement these things from scratch. You don't have the time. And maybe your code could be filled with bugs, and you don't have the time to debug your implementation rather than your logic. So instead, we will already use a very fast and efficient built-in sort. It actually runs it actually is the combination of two sorts, if I recall. And you don't need to worry about how it's implemented, but all you need to know is how to use it. And the way you do that is by calling the sort function. And this should already be included if you're using our IO templates. That includes this library called bits/standard_c++.h. It's actually spelled bits/std_c++.h. I say standard just, I don't know, because of habit. And to sort, you basically first provide the, sorry, I think, does anyone have a question? Okay, sorry, I think I might have missed.
There's a question in the chat.
Oh, let me have a look. Great question. So vec2.end actually points to just after the last element. And the reason we do so is, actually, let me quickly go over it, is because if you look at the iterating syntax over here, you want to, if iterator pointed to the last element, then essentially, as soon as you reach the last element, you would exit the loop because you'd have it is equal to vec2.end, and you'd not end up printing the last value. So it actually points to just after the last element in memory. So as soon as you do it++, you kind of move on to the last element. And over there, you've exceeded the last element, you can now break out of the loop. So it gives you a nice condition to break out of iterations. And that's kind of exactly why it was made this way. So I hope that, okay, awesome. Great question, and thank you for asking. Okay, so yeah, so you basically, to sort, you basically pass in the pointer to the beginning. Again, you just need to remember the syntax, vec2.begin, comma, vec2.end, which is sort of like our representation of the ending of the vector, although it's quite not that. If you want to sort these integers in descending order, you can use this built-in function called the greater int function. And this allows you to actually, so normally sort will try to do stuff in ascending order. Its definition of ascending order. Like it has this definition already made up for strings, for integers, exactly what you think. But if you want to do it the other way around, you can use this thing called a templated function. And you don't need to know what that is, but just remember the syntax or just look at it, refer to the slides for it. But it's greater int, which kind of tells you, the int tells you what the data type of the vector is. And the greater function is basically just doing the opposite of the less than function. It's a built-in function, so you don't need to, it's not something you have to implement. There's also this cool thing that you can do with custom comparison. Maybe you have some weird data structure that you're trying to sort. And C++ doesn't know how to sort it. This is something you came up with. And you can actually provide your own custom compare function that tells you what the order is. Like, why is one data structure, or why is one object bigger than another object? For example, you could have an object that details a person, and then you could tell me why one person is less than another person, which is quite a sad thing to say. But maybe it could be height, you never know. And over there, we're not going to go over the syntax of a custom compare function, but if you have more questions on how to implement it, over the syntax, happy to answer it in the breakout rooms. All right, so hopefully you know how to use sort. You just need to know the little function that we just gave you. And with that, you should be able to tackle problem C, planting trees, which is our last problem for the workshop. But that doesn't mean the workshop's over, because we're going to be going over the weekly contest. So we really hope you stay after this problem. But anyway, have a look at this problem. Hopefully we'll give you guys about 3 to 5 minutes to read it, 3 minutes to read it, and then we'll go over the sample input together and the hints. Great. So as soon as you read the problem, which we'll actually break out into breakout rooms where you all can work together. And I think all the officers will go through the sample input together independently in all those breakout rooms. And you're free to unmute, free to talk to each other. Please, you're more than encouraged to work collaboratively. So you're not competing against each other in these example problems, or even the weekly contest for that matter. And that's kind of what we want to encourage here, for you guys to work together. So yeah, I'm gonna pause recording just so that it's easier for me to post the recording later. All right, so let me go over the sample input, and then we'll break for breakout rooms where you have some more time to think about it. Okay, so the first sample input, it tells you that you have 4 trees to grow. The first one takes 2 days to grow, the second one takes 3, the third one takes 4, and finally the fourth tree takes 3 days. And we want to find the right way to grow these trees so that we reduce the total amount, the amount of time taken for the last tree to grow, so that John can start planning his party, can start organizing his party. So here's one order. Maybe on day 1, let's plant the tree that takes 3 days. That could be tree 2 or tree 4. I mean, really, the name of the tree really does, the number of the tree really doesn't matter here. So we have 2 trees of that takes 3 days to grow. So let's take one of them. Let's grow them on day 1. On the first day, we know that John is a really lazy farmer, so he doesn't end up growing anything on the first day. He just plants the seed, I guess. And then it takes 3 days to grow. So the tree ends up growing on day 4. While that tree is growing, John could grow another tree. So he takes on day 2, he plants another tree and maybe he takes the tree that takes 4 days. So that starts on day 2. And takes 4 days to grow and ends up growing all the way, ends up growing fully on day 6. Then on day 3, he similarly repeats the process, but he takes the other tree that takes 3 days. And again, that finishes growing on day 6 because it's just 3 plus 3 plus 1, that 1 extra day to plant it, as according to the problem statement. Finally, on the 4th day, he plants the last tree that he had, and it also ends up fully growing on day 6. So as you can see, looking at all the trees together, tree 1 will finish growing on day 4, tree 2 on day 6, tree 3 on day 6, tree 4 on day 6. So all the trees, as you can see, end up growing by the end of the 6th day. So John can start organizing his party on day 7, and that's exactly what the sample output tells you. Note that there are multiple possible solutions. I will let you think about the other ones, but this is the most optimal one. And yeah, let's actually break for breakout rooms, and where the officers can immediately go over the hints, and then we'll give you maybe another 5 minutes to just talk to each other about it, and then we can reconvene for the solution. Okay, let's get right into. Hopefully the officers kind of went over the hints, but let me just go over it real quick because they're kind of important for the solution. The idea is to think greedy, and by greedy here we mean is that you don't really worry about the rest of the problem. You kind of make the locally optimal choice, and we'll realize what that means in a second. And turns out, being greedy and making that optimal choice at each step ends up in an overall optimal solution, and you don't really need to worry about the entire problem at once. So what you're going to be greedy about is choosing which tree to grow first to minimize the overall time. And how do you calculate the maximum amount? And then the other hint is, how do you calculate the maximum amount of time you must wait for all the trees to grow? So let's first tackle bullet number 3, which tree should John grow first? And then we'll easily be able to find the maximum amount of time with some really quick code. Okay, so the solution. All right, let's see. So I'm going to actually claim that it's optimal to plant the tree that takes the longest number of days first. So in sample input 1, you might have seen the trees 2, in no particular order, but I believe it is 3, 4, 3, and 2. I say that we should always grow the tree John should always grow the tree that takes 4 days to grow first, followed by the tree that takes 3 days, followed by the other tree that takes 3 days, and then followed by the last tree that takes 2 days. And you might be asking why. One of the goals with beginner CP is to be more rigorous about problem solving. So I'm gonna try to prove this more formally. And this is gonna be a really simple proof. Don't worry about it. But consider, and this is gonna be super informal, but if you have more questions about really how to formally prove this, this kind of comes up in CS 180 that you'll end up probably taking next year or sometime. But I can give you a good intuition about how you end up proving these things, which is pretty cool actually. So feel free to ask us during the the breakout rooms after this. But consider if you planted a tree with fewer number of days first. So maybe I'm wrong, and maybe you grow the tree that took 2 days to grow first. So firstly, notice that the day on which the tree is fully grown is just the current day plus the number of days the tree takes to grow, right? Plus 1. Because if you grew a tree that takes 2 days to grow on day 2, then it's going to end up being fully grown on day 5. So that's 2 plus 2 plus 1. I'm forgetting the plus 1 here on the slides, but you have that extra day that John takes. Okay, so maybe on day 1 I decided to grow the tree that takes 2 days, and then on another later day, maybe like on day X or something, I decide, which is greater than 1, I decide to grow the tree that takes 4 days, which is more than the number of days. I could easily swap these 2 trees, so I could end up growing the tree that takes 4 days first, and that you can only get a better solution, because the tree that takes 4 days to grow, you'll end up adding 1 to that, because it now grows on day 1. And the tree that takes 2 days to grow will now end up being added to X, because X is the day on which I'll grow that tree. So X plus 4 is obviously greater than X plus 2. So when I move the tree that takes 2 days to day X, I can only increase the maximum number of days at which John can start organizing the party. And if this, if this kind of hard to follow, just kind of try to draw it out. So for example, suppose you grew the tree that took 2 days first, and then maybe a day later you decide to grow the tree that takes 4 days. Well, if I actually swap the 2, then the number of total days, the maximum of the total number of days can only become smaller, because I end up shifting the tree that takes more days to the beginning. So it can only take fewer number of days in total. And if you want to look at this more, mathematically, where we consider, where we actually make the 4 and X variables and look at inequalities, we can do that during the breakout rooms. And, I think that'll be super instructive as well. Something to know when you think about greedy solutions is that sometimes it's hard to prove why this works. And, in this case, it's sometimes easy to get the intuition, and this meme sort of, from Pawnstars kind of realizes exactly what's going on. And sometimes your coding looks weird. It's an unproven greedy solution, and greedy solutions always seem really nice. They're like, I really wish this could work. And sometimes they do, but sometimes they don't. And your goal sometimes would be to either prove that it doesn't or find a counterexample for it, which is like an easy way to prove it. So you could rack your mind head a bit and find some case for which being greedy doesn't really work. And we're gonna look into some problems in which greedy definitely doesn't work in next workshop. So yeah, so how do you get the longest trees first? I mean, I hope I've been able to convince you to grow the longest tree first. Well, we pretty much did something for this, and we could basically just sort in descending order. You take the input into a vector and just sort it. And the template for this problem should have hopefully taken the input in this as a vector, and then you just need to call sort on it. And you basically just grow each tree in the same order as they are in the vector. And now you kind of get, now you kind of want to find the maximum number of days required across all the trees, right? Because if you grow, say, the tree that takes 4 days on day 1, but then you end up growing some other tree, like say a tree that takes 3 days on some later day, that could actually end up overshooting the maximum. So you want to consider the maximum across all trees. So you don't really know what's going to be the last tree that's going to be the one to fully grow before John can start organizing his party. So you need to take the maximum across all trees. And let's kind of go over the code to see how we do this. The first thing is you take it as input. Hopefully this is this is familiar to you from the coding template. You just take it in as a vector. Let's call this vector trees. And let's sort it in descending order with the syntax I showed you before. So trees.begin, trees.end, and greater int, and we call the sort function on it. And then for every tree, once you've sorted it, remember that when you do the sort, it happens in place. So now the same vector trees contains the elements in the new order. And to each element of trees, let's add them. So I basically over here in the loop tells you the number of the current day that you're at. So for example, if you were at, if you're at tree sub I, and let's say you had the same example as sample input 1. So when you sort it at I is equal to 0, you're going to have the tree that takes 4 days. So trees sub 0 is equal to 4. And then let's go ahead and add the number of days to it, which is I plus 1. And this kind of this is basically doing the exact same thing as the plus 1 tells you, the amount of time John takes to grow it, and I tells you the current day. And then once we have, and this is basically this now tree sub I is basically going to contain the maximum number, basically the day at which the tree is going to be fully grown. And now you kind of just want to find the tree that takes the most amount of time to be fully grown. Which tree takes ends up growing on the last day in our sequence. And C++ actually provides this really convenient function here. You might not have seen this before. It's not something that's taught in class in CS31 or 32. But you have this function called max element, which ends up taking, again, the beginning and the end of the vector and returns an iterator to basically a pointer to where the maximum element is. So again, since it's a pointer, we kind of use a star notation to get the actual value. And this is a really convenient function because I don't have to, normally if you want to find a max of an element, you kind of keep track of what the current max is, you compare it to the current element, and if it's greater, you replace the max with it. But instead of having that for loop, I could use this really convenient function called max element, and I would encourage you guys to use it in all the workshops. So once you get the max, the last day on which any tree is fully grown, we just add 1 to it because the problem told us, that John can only start organizing the party on the next day. So let's just add +1. And yeah, that's actually the entire implementation. Hopefully that made sense. If you have any questions, we're just going to break out into rooms for the example problems and the contest problems. So hopefully we could help you out there. But yeah, so the workshop still isn't over. Let's not start dropping here. But before we move on to our contest, and I really encourage you to stay for the contest and solve problems together, let's take a minute to just fill out this feedback form. We really encourage all feedback. Any good, any bad. If you think the problems are too easy, the problems are too hard, you want us to cover something that you think is interesting. Maybe we had some problems with logistics. Any sort of feedback you have, we're more than happy to hear you out. And we're just going to wait maybe 2 minutes for you guys to fill it out, and then I can share the contest link and we can get started. And sorry, a quick detail on the contest. The contest will run for a week, so until the next workshop. And according to the poll, I will let you guys know when that is on Facebook. And so yeah, let's give you 2 minutes to fill this feedback.